Hi, hello everyone. Good evening to some and good morning to some. So, can you hear me clearly? Is my voice audible to you?
Yes,
Alright, so I will be muting all of you. Alright, so we'll communicate by chat only. Alright, so the voice is clear to all of you. Great, great, great. So, who all tried the quiz which is on the session 1? In case you did not log in, I'll just show you around. Here you have to go to no big data. Okay, the recording has been started. Good. All right. So in case I miss out on recording, please remind me. Yeah. There are few points. There are few points which are not yet covered. Okay, because there was too much on the first session, so I have moved some of the MapReduce part and Hadoop architecture part to today. I mean, actually 50% is today. All right. So you click on my courses, and then whatever courses you have appeared for or you have taken, they will appear, and click on the course you like. I mean, course the one 24 January one. Under that, you will have this quiz link. You can click on take quiz, and you can attempt multiple times. All right. That will generally what happens is, although we keep record of all the attempts you make, but if you take it multiple times, it actually improves your knowledge. It makes you remember it better. So the overall objective is to learn. All right, so let me close my. All right, so here we are. All right, so let's start with recap. Yeah. So for yesterday's recording, I am very sorry because what happened was, at the end of the session, my system hanged, and I'm actually happy that at least audio recording was proper. At least something came out, because what I was suspecting is everything will get lost. So this rarely happens on a Mac, but it did happen yesterday. So everything froze. I had to hard boot the machine, and I'm lucky that we still have the video and the audio. Okay. Yeah. So the best way is to use the PDF by yourself and use that parallelly. Okay. Yeah. All right. So I'm extremely sorry for that. And so, all right then. So let's start with the recap of the HDFS architecture. So basically, there was something called name node and something called data nodes. Name node is a single entity which keeps the metadata, and data nodes are the one which keeps all the file information. Files are broken down into blocks, and these blocks are stored on the data nodes. So every client, when it comes in, it asks name node whether the file is there or not. If the file is there, the name node gives you the location of the data nodes. All right. This way, the client directly talks to the data nodes and gets the data from each data nodes, assembles it, and gives you the data. Client, when I say client, is either the command line client, or it is the or it is the mm, driver which you are using from program. All right. So this is the way HDFS works in general. Now, moving on to the next step, which is compute engine. All right. So a compute engine essentially is the one which is responsible for doing all the computation, as in whether you want to sort the data, search the data, and locate some information, doing such certain computation, and all of that is the responsibility of the compute engine. Okay, so compute engine, let's talk about something called yarn. Instead of talking about detailed architecture of yarn, we will just go with the basic model which was followed in yarn. Okay, so let's start with a simple problem to you. Okay, now again, back to a very simple problem. How much time do you think it will take to sort 1 terabyte of data using a 1 gigahertz processor? It's a simple question. Okay. And why do I ask about sorting? Because sorting is the mother of most of the problems. Sorting is the basis of lots of problems which you do day in day out. For example, when you query the data using SQL, saying when get me all the records which have this column equals to this value, there you will get all the data, and in case the data is not indexed, you will not get really good performance. So, and what is indexing? Indexing is essentially keeping the data sorted i- in a separate place so that lookup can be really faster. Okay, so a where clause which is operating on a indexed column is essentially a sorting problem, because if the data is not sorted, searching is really slow. Okay, so every searching problem is generally a sorting problem. Okay, now the second aspect of a sorting algorithm is, say when you try to join two data sets. Okay, when you try to join two data sets, you are essentially looking up for the records of one. You are essentially looking up for the records of one into another table, right? So sorting is used even in the joining of the two data sets. Now the third place where you will see the sorting is in order by clause. Whenever you say order by this column, it essentially uses sorting beneath the hood, right? And also, so where clause, join clause, and then order by clause, and group by. When you group by a table, you are also going to use you're going to use the sorting indirectly. You will sort the data, I mean database will sort the data for you, and then it will group the values which together which have the same key, right? So sorting is a very important problem. Whenever you do sorting, you uh, I mean f- whenever you are building any system, it is the sorting which is of very most consequence whenever you're building an architecture. So that's why I ask this question. So if you are given 1 terabyte of data and You're given a good enough processor, good enough RAM. How much time do you think it will take to sort 1 terabyte of data? Anyone? Any wild guesses? Abhinav says 30 minutes. Anybody else? Okay. 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 Oh, it was in. Have I mentioned it somewhere? I doubt if I told this in the yesterday's session. I don't remember if I told. But yes, it is there in the quiz. Yeah. Good. So, okay. Okay. So, nevertheless, the important aspect is that you remember it. The important aspect is you remember it. And that's important. I'm happy. So, it takes around 5 hours. All right. So, for some, it sounds impossible. And for some, it sounds like it will take maybe a couple of minutes. But the truth is that sorting takes time. Sorting takes time. As the number of records grow, the sorting time also grows, although it grows faster than the number of records, right? So sorting takes time. And what is problem with these 5 hours? First, we need faster search. Second, we might have to sort bigger data than 1 terabyte. Third, we might have to do it more often, right? Therefore, therefore, we need to build a better search sorting mechanism. And that is why the whole of the compute engine's core is most of the engineering of yarn or MapReduce has gone into sorting of the data. The whole MapReduce is essentially a grand sorting engine. Okay. For example, and sorting is such a problem that all these technology companies compete on sorting. So Google, as per the last record in 2011, 8 September, although I'm not aware of if they ever published their statistics afterwards, but it took Google 6.5 hours to sort 10 petabyte of data, okay, on 8,000 computers. All right. Sounds strange to you? No? So basically, all of these companies are working on improving sorting, and Hadoop has also been the winner in this game. Why? Because sorting is a big problem. All right. Therefore, sorting was built from bottom up to solve these kind of problem. To sort 1 terabyte of data, if we have to do it 5 minutes, no matter what RAM do we use or no matter what processor we will use, we will not be able to go beyond few hours. We might go up to 2 hours, 1 hour, but nothing beyond it. Okay. Therefore, if you want to go beyond few hours when you want to sort 1 terabyte of data, you might have to take additional steps. you might have to build a system which can sort that data really, really fast. Okay, and that can only be done using distributed computing. All right. So let's discuss a little bit about the compute engine. The core components of the compute engine, although it is no longer called MapReduce, we'll just say core component. Okay, for time being, let's just call it MapReduce one. Okay, so this is the architecture of MapReduce V1, Yarn V1. All right, let's understand it. The way we understood the computation earlier, okay, storage earlier, we had name node and we had data nodes. Similarly, we have in the compute engine, we have job tracker and task trackers. Okay, and whenever we want to get something done, we tell job tracker, and that job tracker assigns the work to each task trackers, and each task trackers do the job and give you the feedback. Okay, now in other words, in another way, if I have to represent it, it would look like this. There is something called job tracker, there is something called task trackers. Task trackers are multiple, job trackers is single. All right, and this is the flow in which you get your work done on a job on a job tracker. Okay, so a client comes in, the first step it does, the user, the end user, you, okay, you will first copy your data onto DFS. Okay, DFS is HDFS. Second, you will submit the job to the client is Hadoop client. Now this Hadoop client will talk to DFS, get all the information about the input files. Now, based on this information, it will form the splits. Okay, we'll talk about splits. All right. Now, let me again describe this diagram. I think I missed something. So you have job tracker and you have task trackers. Okay. You tell job tracker to do the work. Job tracker delegates the work to each task tracker. And on what basis does it do the delegation? Based on where is the data available. If the data is only available of on first two nodes, then job tracker will only assign the work to the first two nodes. Okay, so each task tracker is generally running on the data nodes. Okay, each task tracker is generally running on the data nodes as well. So each machine which is designated for data node generally have these two processes running on it. One is task tracker, other is data node. All right. So whenever you are assigning something to the task tracker, it is basically manipulating the file which is located on the data node and giving the work back to job tracker. All right. So So whenever you are assigning something to job tracker, you tell job tracker, I want to process this particular file. And this file might be located on multiple data nodes on single data nodes. Okay. So if that work is that if the file is those if you remember we talked yesterday about blocks, those blocks might be available on few data nodes and so on. So it takes the benefit of that aspect. All right, so there are two things task tracker job tracker did for you. Two things MapReduce engine did for you. First, it took the data. First, it took your computation to the data rather than taking the data to the computation. Right. Second, it distributed your work to multiple nodes so that the execution can be really, really fast. Right. That's what job tracker did. All right, that's what the whole paradigm did for you. So it is obvious that job tracker need to know about name node, and from there it will gather the information about data nodes. Now look at this, right? Here, once the client, once you submit the job via client will talk to the name node, find out all the information about where are the pieces located or where are the blocks located. On each block, it creates something called a split. Okay, just remember that for each block, it creates something called a split, and based on that is input split, job tracker does the work. Okay, so client basically collected the information from DFS and then gave that information to job tracker. Now job tracker will start working. Now job tracker will start reading the more information about the files. Okay, also it will read the job files in which you have described what needs to be executed, and after that it will create the maps and reduces. What does it mean by maps and reduces? It basically initialize a job queue. Just like in a hotel, whenever you make an order, there's a job queue. It puts the job queue there in the job queue, your order paper, as well as one copy goes to the kitchen where it gets cooked. And once it comes back, it marks it there that this job is finished. Similarly, here, job tracker initializes a job queue saying that these are the jobs which are running. And for each of the job, so right now we are talking about a client called Hadoop client or driver we are talking about. All right. The client could be Pig. You are very right. Client could be Hive. Yes. And client could be your Java program. Good. Good question. Yeah. Now, all right. So let me go back to the step number 4. Here, so don't worry about splits as of now. Basically each block need to be converted into a meaningful data, and that meaningful form is called input split. We'll go into the details later. All right, now once this input split information is gathered, then the job information is pushed back to the HDFS, and then the work is given to job tracker. Now job tracker will read those files from the HDFS and start working upon it. Okay. Although these dynamics keep on changing a little bit. Now the next thing job tracker will do is create the mappers. Why? Because in the job, when you submit a job to MapReduce, you basically write your logic in two forms, maps and reduces. Maps run on each node and reduce is the aggregation. We'll go into the details of maps. So maps is a logic which needs to be run on all the data nodes where data is present. Okay, so these functions for maps and reduces are created and and assigned to each of the task tracker. Okay, that you need to do this. We have to assign these maps. Maps is basically a connotation of a function which you have given. Okay, you have, when you submit a job to MapReduce engine, you essentially say that hey, this is the function which in which my map logic is there, and this is the function which contains my logic for reduce. Okay, now this logic which you have written for map is goes to all the task trackers which are located on the same machine as your data. All right, and then once all of the maps finish their work, they the job is updated. Job queue keeps on updating whenever a map job is finished. A job queue is updated, and once job queue is updated, then all the things finish in job queue, the response goes back to the client saying I'm done. Okay. In the meantime, this job tracker keep pinging each of the task trackers who is doing the work. All these task trackers are doing the work, and this job tracker keeps on pinging them. Hey, how are you? Are you fine? And that mechanism is called heartbeat. In case any of these task tracker go down, job tracker instantaneously discards the work it has done so far and shifts the work to somebody else. Okay. So let's say that in the job queue there are these four task trackers who are working on the data. When I say working, they are essentially executing your map function on some blocks. So first few blocks on task tracker 1, then next two blocks on task tracker 3, next two blocks on task tracker 2, and next few blocks on task tracker 4. Okay. So these blocks are being processed on each of the task trackers. And and what do I mean by processing? It is essentially running your map function which you have submitted on top of that data. And once all of this finishes, the output goes back to the job tracker, and client is updated the job has finished. Okay, we'll go into map reduce in a little while, no worries. Okay. So this mechanics is clear to you, right? We essentially are saying that any computation we want to do is near we send it near the data, and second we send it on multiple machine, so that multiple machines are working on your o- on top of the data and giving you the response. In case any of the machine fails in between, the task is quickly assigned to some other machine which is closer to the data. Okay. So task, the order of when you are assigning the work to the task is generally assigned to somebody who is very very close to the data. And in case that task tracker is very busy or down, then the work is given to any other node which is maybe on the same rack, or maybe on the same data center, or it may be in the different data center, but the order remains that first it tries to get the work done on the same machine which contains the data. Second, it tries to get it done on the same subnet or same hub, or you can say same rack. If it doesn't work out, then at least it tries to do it on the same data center. If that also doesn't work out, then it tries to execute in the different data center. Overall idea is to avoid the data transfer as much as we can. All right. So this was the mechanics. This was the mechanics of a general compute engine. Now let us talk something about MapReduce. Okay. So MapReduce is a paradigm. MapReduce is a way of computing, right? The way you have SQL in which you write select star from something, and then you can only do set based operations, right? You generally don't do, you don't generally iterate over the records, you don't generally look up the record by of your own choice. So you generally don't do in case of SQL, right? So similar to that, you have a new paradigm of MapReduce, where you write this is a more constrained environment for people, where they need to basically write two kinds of functions. One is called map, other is called reduce. Okay. So a map is basically, the function map is basically run on each of the nodes which contain your data. So you will write a function called map, which takes input data and prints out something. And that something is sorted. That something is sorted and then copied to a central place and merged together. And after merging that data, that is given to your reduce function. Okay, this reduce function is something you wrote, right? So this is something you wrote, as well as reduce function is something you wrote. All right, sounds good. So on top of each of the HDFS block, a split was created. On top of each split, map will be run, and whatever is the output of the map is in the generally in the form of key and the value. Why key? Because key is the basis of sorting the data. And once that sorting happens, it goes to a central machine and then merged together, and it is then given to your reduce function in the form of key and values. For a key, there would be multiple values, some from here, some from here, some from here. And once that all data gets merged, that is passed through this reduce function. And then the output is saved to the HDFS. Okay, so here, this part of, you see this color, bluish color, this this portion is what you control. Rest of it is controlled by MapReduce. All right. So this was sort of an architecture of Hadoop 1.0. Okay, where the only way of computation was in the form of MapReduce. Okay, you could only write your program in the form of MapReduce. Okay, while so basically a MapReduce was doing three things at a time. First, it was running your logic on multiple machine. Second, it was running your logic closer to the data. Third, it was trying to do only the map reduce kind of a paradigm. It was only allowing us to map reduce, write our work in in the form of map reduce. Any problem you have to break down into map reduce. That was Hadoop 1.0, right? So there were three things which it was trying to do. First, distributing work to multiple computers. Second, taking the code closer to the data, and third, trying to do the sorting for you. Okay, now MapReduce was only the way earlier in Hadoop 1.0, but now there are there are multiple layers. The MapReduce framework is broken down into two portions. One is pure MapReduce, and second portion is Yarn. Yarn is responsible for first two works, meaning giving you capability of assigning the work to each each task trackers, okay, and giving you the capability of taking the code closer to the data. So the distribution of the computing or the computation part is absorbed by Yarn, while the paradigm of MapReduce is separate portion altogether, which depends on Yarn. Now, what did it do? Yeah, yeah, we will go through this slide again. No worries here. Okay, all we did was we run our logic on multiple computers. Then Hadoop sorted the output of map. I mean, whenever, what does it mean by running the logic? Basically, our program gave the output in the form of key value pairs. Key and value can be any object. Now, based on key, the data was sorted and it was merged at single place. After merging, each of the key and all of the values were aggregated together, and given to your reduce function. The reduce function operates upon that and gives the output. All right. So that logic, the whole mechanism of this key value pair and sorting was given to MapReduce, right? So as we discussed, though sorting is the most important thing, but it's not the only thing in computing, right? That's why the sorting part was given to MapReduce as separate, while yarn remains as the pure distributed computing, distributed computing block, meaning any work you give yarn, you can tell that running on these computers, get and then give it back. Though as an end user you may not be using yarn, but you will be using yarn indirectly if you are using MapReduce or other data processing tools. Now this simple modularization made a big impact in the world of Hadoop. That is why nowadays you see things like Apache Spark and things like Apache Tej and things like, you can see a lot of these things. All right. So HBase was basically basically yarn is something which is used by other paradigms also, not only MapReduce. So this was a big revolution in the history of Hadoop. Okay. All right. Now, similarly, the job tracker, task tracker, which we discussed, they were broken down into these parts. Okay, so you have something called resource manager, which is equivalent of your job tracker, to which all the clients talk, and this resource manager talks to each node manager as well as talks to something called app master. App master is something which is per application. Okay, per application meaning one for MapReduce, one for Spark, one for Thais, all kind of the whole logic of each of the paradigm, each of the framework resides in app master. Okay, app master is basically container is something which runs app masters and gives the result back to the resource manager. Okay, so all the containers keep on running on. So basically the same design was broken further and made more modular so that you can get the you can run any kind of logic. So if you want to build something today which is similar to MapReduce, you can build your own app master with which will be run inside the container and then on each node. Okay, so this is what happens. All right, this is what happens. So this is the architecture of yarn. We will go into the architecture of yarn in maybe later once again, but this is more or less good enough for you to start working on on the Hadoop. Okay, so you have resource manager. Resource manager is the one which is the central point of managing the resources on the whole cluster. Now resource manager keeps talking to node managers, which are basically responsible for managing the node and running the containers. And each container is running the application logic specific to each of the frameworks. Okay. Now under app master, you generally give your code to app master. I mean, when you say you execute something, app master executes it and gives back the results. So this is the architecture of, right. So it is not necessary to have app master and container on all the nodes. They keep on moving based on the demand, based on the availability of the nodes. All right. That's a part of the framework. All right. So this was a quick overview of yarn and MapReduce. So do not worry about the MapReduce part as well as getting more details about yarn. More important part here is understanding that how we will be dividing our work into MapReduce to get the results. All right. We'll talk about few problems and then we'll try to convert them into MapReduce paradigm. All right. But before that, let me give you an overview of our cluster. So first, let's see the status of our cluster as of today. You can see the status here. All right. So this is called Ambari. Okay. This is called Ambari. It is basically a diagnostic center. You can see what's going on, right? And you can see right now, say Uzi server is down. We have stopped the Uzi server because we don't need it right now. But and Negios is stopped, but we can start the Negios. Okay, and where is our Negios? Okay, all right. So it's getting started. Second, you can assess it. Other than this, let me. Okay, web interface. We talk about Ambari and Hue. Remember, here we are connected to this hadoop1.nobigdata.com colon 8080. If you want to operate or interact with any of these services, also let me give you an overview of various services before I move to something. All right, you see this? There is HDFS disk, uh, and there's so many data nodes. This is a cluster node, and these are the services running. In case in case you want to relocate the service onto somewhere else, you can basically say service action and then say move this particular service to somewhere. Okay, so that is the role of Ambari. And easiest way to install Hadoop is probably via Ambari. If you are trying to do it locally, you can use a virtual machine, but when you are trying to install it on a cluster, instead of using Cloudera Cluster Manager, I have preferred to use Ambari. All you do is install Ambari agents on all the machine in the network, and on one machine you install Ambari server. Once Ambari server is up, you will see this interface, and then you will start installing one service at a time, and automatically everything will be installed. Okay, so remember that using Ambari you can do a lot of magic, lot of whole cluster management you can do from here. Okay, so here it says that one of the data nodes is having the space issues. Okay, now this way, so it keeps on monitoring all the time. Now if you want to interact with any of these services, you can use a service called Hue. Hue. It essentially provides a single interface to connect. So you can browse the files like this. You can, when you're working, don't tamper with somebody else's data or work. Just create your own folder and then work. Okay, you can create a directory from there and then upload the data. All right, but you can have a look without damaging anybody's data. So this is some Srivasan's data, and these are the results of his MapReduce job. Right now, so that was, now the next way is the way we are going to work. So Ambari you can basically install if you just go to Ambari. Okay, although you don't need to install, but when in the if you are really interested, you can have a look at installation guide for Ambari. This should be sufficient for you. All right. Similarly, the way we have interacted with the file browser, these are the folders, and we can copy, move, change permissions. We have something called to interact with Hive. We can write our own queries here, saying create. I mean, this is my table list. Okay, and here, not this one. Okay, you can create a database using Hive. You can create tables. You can manipulate a lot of things. If you want to execute If you want to execute something on Hive, you can use the query editor. If you want to execute something in the pig, you can execute it from here. Similarly, you can schedule your job, but Oozie is not yet working, so we'll have to start Oozie before that. And these two things are for Oozie. This one is to browse the jobs, what's going on our cluster. So basically, the Oozie is not running, so job browser you can't see much. Right? So we can interact with Oozie, HDFS, Hive, and Pig from here. Okay. Now, other than this, can you see my screen clearly? Is my screen clear to you, or should I increase the font? All right. In case you are on Windows, you can use Putty to connect to the server. Otherwise, if you are on Linux or Mac, you can simply say ssh student at hadoop1.nobigdata.com. You can also connect to Hadoop 2, Hadoop 3, Hadoop 4. Okay, because from anywhere you can talk to HDFS, or if you talk to MapReduce, it will be the same scenario. Or you talk to, because all of those clients are going to talk to the same Hadoop. Okay, so to interact with Hadoop, we generally use this Hadoop client. You were asking, right, that what is client? This is the client. So Hadoop fs minus ls. Okay, so the most important two commands from Hadoop is Hadoop fs, which basically execute any hdfs commands. Okay, so here it is. So we are able to see the hdfs files. Okay, and the other important command from Hadoop is Hadoop jar. Using this, you can execute a jar containing your MapReduce logic, right? Now, that's how you do. Now, how do you copy the data to and fro the HDFS? Okay. So remember that whenever we are copying data here, right now I am on which server? On Hadoop 1.nobigdata, right? I'm not on my local machine. So if you want to copy something from your local machine to HDFS, first you will have to copy locally to Hadoop 1 and then use Hadoop. And so let's say I want to copy a file called xyza.txt. Okay, this is my file. Now I would say Hadoop fs minus copy from local. Okay, and I say xyz the txt to asgiri folder. This is my asgiri folder on the Hadoop server. Let me show you from the web interface also. Not this one, we will go to this. Alright, so here there is my folder in the HDFS. You guys should create your own folder as we're talking. All right, do you see my folder somewhere? Good, it's here. Nice. So here there is no file called xyz xyz a. Now I'm copying this file from my local machine with local machine is local Linux machine, which is Hadoop one. Because I have SSH'd onto the server. Now here, if you refresh it, you should see that file. Right? Now where is our file? There. It has come. Okay. Now it shows the data inside it. Alright. Now if you want to, what was the other thing we were supposed to do? Yeah, if you want to create a directory, you can say Hadoop fs minus make directory, and we say sgiri temp. Okay. Now the directory will be created over there, not in this, but one level up, as in the students folder. So here there will be a folder sgiri temp. You see this? So that's my folder. All right. So this way we were able to talk to HDFS using our Hadoop client. Okay. So we did not have to worry about blocks as of now, and we did not have to. Yeah, you're right, Seema. We can actually run most of the commands. Basically, Hadoop is designed in the same way. Commands are designed in the same way as Unix. As you can see here, you can see that there is something called append to file, cat checksum ch group ch mode ch own, copy from local, copy to local. Copy to local means we want to download data back. And then you have count, copy copy file from one location to another location on HDFS itself. It doesn't, it basically from to and from inside HDFS only. And then create a snapshot. Df is similar to your normal df. You can see the df. Okay. Df shows your the disks mounted. So this is my file system. Okay. Hadoop 1 is having this many, this big size, and out of which this much is used. Okay. Okay. So out of 124 GB, 16 GB is used, and 13, this much is available. While, now look at this, look at this, while local system says it's only 60 GB in hard disk. Okay. So 124 GB is essentially after adding all of the disks of four clusters. Since we are using SSD, solid state hard drive, for the faster response, the disk storage is fairly small. Okay. All right. And then to run a map reduce command, you can, right? Now we have talked about all of this. We have also talked about, if you're on Windows, you can use putty. Okay. There is some other command somebody was telling me the other day. I forgot the name. there is a nice terminal as well, similar to putty. Okay. And for copying the data, if you're on Unix, you can copy that. I'm on Mac right now. If I want to copy my data from my local machine, which is uh, laptop, from my laptop, if I have to copy the data to this Hadoop one, I can use a command called scp. Okay. So if you want to move the data to HDFS from the command line, you will have to take two steps. First, you will have to copy the data from your local laptop or somewhere else onto Hadoop one. So my local laptop to Hadoop one, and then the second step would be to copy the data to HDFS. These are two steps. But using the browser, you can do it in a single step. Here, you can say upload. All right. So if you want to copy something onto Hadoop one, you can use SCP. Let me take an example. All right. So I don't know what to copy. Okay. So let's say, let me copy some file called hive udf onto Hadoop one dot no big data dot com slash s. Okay. So it's copying my data to over there. Let me see what error do we get. Oh, I have to write a student here. Student. Then it will ask for password. Now it's copying. All right. Now the next thing is you can use these commands. All right. We have done this. Please create your own folder to put your work. And remember that since it's open to other students, so other student might fiddle with your data. Okay. So be aware of that fact. Avoid writing some, avoid uploading something personal. Now you can execute a pig command like this and hive command like this. Okay. All right. But right now I'm not going to get into it because that will anyway be covered in later sessions. But you can execute. I'll just show you. So we were able to copy the data. All right. Now let's go to sgiri folder here. This sgiri is my local folder. It is not the folder which is on there on HDFS. Okay. Now this is the folder. Now parallelly, if you want to run anything on pig, you can say pig and start working on that. Okay. Here you can start working on this. Right. So this is your pig command. All right. And you can say ax is equals to load my data, and you can start working on that. All right. And so on. So this is pig. If you have to run hive, you can run hive from here and then start using SQL commands such as show databases, it shows you the databases, and show tables, you can see the tables, and so on, right? Similarly, if you want to interact with HBase, you can interact from here using HBase shell, and so on. We'll go into the details of individual. Okay, no worries. I'm just giving you an overview so that you feel at home with the environment. And notice that most of the commands which are built, most of the tools that are built, every tool when it comes to the backend or data analysis has a command line interface. All right. So this is the way you can run your MapReduce. So here, this is basically running this particular command and then giving out the data. All right, no worries. Hive commands are exactly like relational databases. They are exactly like databases. You have all the select queries. It's a standard ANSI 20, I think. It's ANSI 20 standard for SQL. ANSI SQL 20. That's the standard, right? Now, so we just went through a quick exercise. If you want to have a look at what does it look like when you run a query, so you say Hadoop jar, okay, no worries if you are getting an error because you were supposed to get an error, okay. So it says Hadoop jar and then the file, the code, okay. So it says Hadoop. Hadoop is the client, jar is the command which we are going to use to execute a jar. And what is a jar? Jar is a kind of a file which is a package of all the files inside it. It's like a zip file. Okay, it's like the format is same as zip, okay, with the minor additions. So Java basically picks up a jar, finds out which one is the main file to be executed, and executes it. Here we are telling Hadoop to run this particular command inside of the jar and take this file as input and this file as output, right? In case that output exists already, it will give you an error, and let's call it 24 gen. Okay, so now it is starting to run a MapReduce job. Before it starts to run a MapReduce job, it gives you a URL to track it. Okay, it gives you a URL to track the job, what's going on with the job. Okay, while it performs the MapReduce, it gives you a URL to track it. Okay, now it shows you that this is the attempt number one, and the attempt number one is on Hadoop 3, not Hadoop 1. Notice that part. So it is trying to get the work done on different nodes. Okay, here. Now to see the logs, you can see the logs from there and so on. All right. So this was just a very cursory look at there is something wrong with our file name. No worries, we'll look into it again. Maybe our file names are wrong. Now, so till now, are there any doubts? I know there would be a lot of doubts, so please feel free to tell. No doubts. Either I'm very bad at explaining things or I'm really good. That's the reason you're not asking question. No questions? All right. No worries. You will get more curious and more questions as we go forward. All right. So, how many tasks failed? Almost everything failed. Here you can see everything failed. No worries. Maybe we had made a mistake in the file name, but we are not going to correct it right now. We're going to go ahead. Okay. And the examples, the example is available online. Okay. Here you can run that example as well. Okay. But no worries. Let's move on. Okay. So my first question to you is, now, the objective of till now, I just give an overview what is where, how are the tools, what tools are there. That's all right now. But oh, okay, yeah, I understand that. But yeah, so should I go slow when? No, you can try it in your own time. The video is getting recorded. I hope this time it doesn't uh, go bad. In case it goes bad, we might have to do it again. I'm hoping that this time it won't crash. All right, because it has never crashed before. Chances are low. So basically, you can try it at your own time as well. Okay, till the point you get efficient with the command line. Okay, and till the time you get comfortable with the command line, you might have a little bit of you know uh, you'll take more time to actually catch up while I'm explaining. Actually, it's difficult. It's difficult actually while I'm explaining. All right, so that was a general, very, very fast paced overview of what is where. And I've done it fast paced because I don't want to make it so monotonous, because most of the parts you will explore and you will figure out by yourself. Like how to create a file, how to upload it, how to download it, how to create a folder. All of that you will figure out by yourself. Similarly, other commands as will go ahead, you will figure out by yourself. So I just gave you a good entry point. So over the week, will have now after this we'll have 1 week before another session, so you can try out all the things. Now, the most important aspect of MapReduce is the paradigm itself. It is little difficult to get used to the concept and start thinking in terms of MapReduce. So we designed couple of questions, and we designed couple of interactive questions so that you participate and we together solve these problems. And I take you to the point that how do we do it using MapReduce. All right. So I'm going to switch between the two. Okay. I'm going to switch between the two. So get used to both. Both have their advantages. All right. I'll keep on switching between web interface and command line. All right. Now, let me ask you a simple question. Sounds like a very, very programming question, but I want to see your approach. It's very important to understand this part. So, if you had a huge text file, imagine all of the Lord of the Rings books. How would you find the frequencies of the words in those files? You have a huge, humongous corpus of text, say all the Lord of the Rings books, for just for the example sake. But our data is going to be far, far bigger than that. Imagine all the books of all of the world. That's the kind of data we are going to talk about. But right now, for this example sake, how would you find the frequency of various words in Lord of the Ring books? Okay, this is pretty straightforward, and consider it your normal day-to-day jobs assignment. What will you do? What will you do? This is, I'm not asking for specifically programming question. I'm asking for any approach that comes to your mind, whether using Microsoft Excel, whether using SQL, or whether using Unix command, or using some readily available tool. So what is it that you will do, or how would you do it using your programming? Just the approach, not the code. Okay. Okay. So Abhinav is already on the map reduce game. All right. Good. 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 Excellent. So Julie's answer is group and count. Excellent. Excellent. And yes. So Abhinav is into map reduce. Yes. Now let me have a look at Sahu's answer. Break the file into small blocks. Okay. Write regular expression and find Unix. You can and find Unix. You can run grep. Good. Good. Just refine your answer a little bit. Think about your answer a little bit. You are on very close. You are on very right track because I have many questions. If you break the file into multiple parts, how are you going to do find the frequencies? Okay. Now, Seema's answer is split the files into smaller chunks. Let's say line by line. Make a directory, okay, to keep counter and then merge. Interesting. Interesting. I need to understand this approach a little more. Okay. So Amit's answer is also similar. Split your files in a smaller one, count different words, merge all the same answers. Okay. Okay. Okay, so probably all of you are saying that split the data of the file into say 10 lines per file and then do counting in each of this one. Then whatever counts are there, you again merge them together to generate an output. Is it? So right now if you had to do just the 10 lines, what will you do? I'm asking for a very rudimentary question that you have just 10 lines and you have to count the words. What will you do? Yes. Feel free, take your time. Yes, yes. So read each word from the input and maintain a hash map, not a list. And if basically we differentiate between a map and a list, list is just something you keep on appending to. Map is like a dictionary which has key and value. Good, good, good. So yeah, that is how we're going to do this. So all right. All right. So whatever questions I had, I got the answer. So first one is create a frequency table or a dictionary. For each word in the input, you increase its frequency in the hash table. And once there are no more words left, you keep on printing. And when I say increase, it means if the word doesn't exist, consider its frequency as 0 and add the word. Oh, you meant dictionary. Now it makes sense. Thank you. To clarify. Okay, okay, okay. Now it makes sense. Good, good. All right. So great, great. We have got whatever answers I was looking for. Actually, I got all of those. Great. Now, so approach number one is the basic rudimentary approach is basically creating a table, a hash table, or a list, or whatever you want to call it. It is essentially a dictionary saying this word exists these many times. So we iterate over one word by word, keep on adding to this dictionary. If that word does not exist already, if it already exists in the dictionary, we increase the count of that one and save it. And we do it for the whole book. And we maintain this dictionary in the memory, right? Now, right. So Amit is talking about a divide and conquer strategy. Okay, yeah, good, good. So in this one, so this is one of the basic primitive approaches which we all do, okay, where we create a hash map and try to solve it using that one. Probably most of the programmers, 90% of the programmers generally rely on a hash map. Okay. So my question to you, did you understand this approach? If you have any questions about this approach, which I'm talking approach number one, let me put a question mark. Great. So do you see any problem with it? What are those problems with this approach? Quickly. Response time. Good. Any other problems do you foresee in this approach? Large number of keys. Good. Time and memory overkill. All the file and hash map will be in the memory. Not really the files will not be in the memory, but completely agreed. Hash map will be in the memory. Going through each word consumes more time and hence delay in response. Good. Memory will have issues in handling big file. Very good. Very good. Very good. So now the problem is with the right? So the problem is that we cannot process the data beyond the RAM size. Agreed? So RAM is something, a memory in which we'll be maintaining the hash table and we'll be doing the lookup continuously in this hash table, right? Therefore, this approach will not be great when it comes to bigger bigger data which does not fit into RAM. And as a thumb rule, the memory consumed by a dictionary is 4 times the actual data. If you sum up all the keys and the value size, you should have to multiply it by 4. Okay, that's the statistics, real statistics about Python's hash map. All right, so basically we cannot process, the RAM is the bottleneck in this game. So if you have 2 GB RAM and if you have half gigabyte of text, then you cannot use this approach. Now second approach is this one. I think one of you already said that. Okay, break the books into one word per per, what do you call it, per row. Okay, in the table you have one row containing one word, and then and then insert it into database. Okay, insert it into database table and execute select word count star from table group by word, right? So will this approach work? If so, what are the problems with this approach? Or before we try to pinpoint the problem with this approach, so there is this approach in which we basically try to eliminate, we are trying to eliminate the problem being faced in handling the memory, because SQL handles all of these things really smoothly without over flooding the RAM, right? So this is fine. Okay, second is a Unix command. Okay, here, so we can do it using Unix also. All we need to do is break the file such that there is one word per line, then sort the data using a command called sort. If we put a flag in this command saying sort 1 GB, in 1 GB, that means it will not consume more than 1 GB of RAM, and then pass it over to the unique minus C. Unique minus C basically counts words in a sorted data. All right. And what is going on here? We started from left to right. One command piping the data. This is pipe. One command piping the data to another command, and then that command piping the data to another command, and so on. Okay. And this pipe, which you see over here, is essentially taking the output of the command on the left and giving that as an input to the command on the right. Okay. Which means that cat file1 file2, all it did was read the file file1 and file2, gave it, after concatenating it, gave it to sed, this one. Sed is essentially a find and replace kind of command here. It's a stream editor, it's a very powerful editor. All this command does is substitute this value with this value. Okay, this value with this value. Okay, and then replace it globally. Basically all it did was replaced space or tab any number of times with a new line. In case you do not understand regular expression right now, go through session 1's regular expression, which I had given to the students because they were facing this challenge. So these all regular expression will get clear, the concepts will get clear to you. So what's going on is, from left to right, I concatenated all the input files, gave it to, replaced tabs with new line, tab or spaces with new line, and then sorted the data, sorted the words after one word, which is one word per line, and then gave it to unique. Will give you, this will give you the word counts of the files. Okay, word counts of the input file1 file2, right? Now What's the benefit of this approach? It says that it will only consume 1 gigabyte of RAM. Okay, so the problem in the first approach, we have tried to solve it using these two approaches, approach 2 and approach 3. Some of you had already pointed out these two approaches. Now my question to you is, now we have removed the bottleneck of RAM. My question to you is, what exactly is the problem with these two approaches, approach number 2 and approach number 3? Okay, just think about for a while. In case you need this presentation, it would be available in the LMS. Okay, so sort is designed in such a way that it will only consume, it will basically sort one, as you guys told, that break it into chunks. Sort breaks the input into chunks, sorts each of the chunks, and then combine them together. Okay, so basically sort will be able to handle the given problem in the given RAM. Okay, so think about it. So think about it, and let me take a break for 10 minutes. Okay, all those sounds like a cheating to you because you will not be able to take 10 minutes break. So think about it, and let's take a break for 10 minutes. All right. All right, so I'm back. Are you guys back? All right, so we were talking about this. Yeah. Results need to be merged again in approach number three. This one. No, actually, that whole merging thing about each chunk of 1 gigabyte is actually done very neatly by sort command. Sort command takes care of that merging. You don't need to merge that. All right. All right. In approach 3, the file needs to be in one place on one computer or we need to merge. So this is all in one computer actually. Processing time will be more as we are doing sequentially. Good, good point, Ranjit. All right. The response time will be outrageous. Yes, true. After inserting every word in the database, which is itself will take time. Yes, querying each row in the database will take quite a lot of time. So here in the approach number two, group by will actually sort the data and will take care of the memory part also. Now, option two, preparing and inserting would take most of the time. Both will take time, preparing, inserting, and group by. Okay, when it comes to gigabytes of data, it takes time to do group by. Yes, you're right. Good. Now, I'm not sure what would be the problem there. Okay, approach number two, insert is very CPU demanding. Excellent, excellent. So, although technically there is no problem as such, but the problem would arise as the data goes high. Okay, so, right. So, the moment data starts growing beyond RAM, the time taken starts increasing, and the following becomes the problem. So, RAM, we actually eliminated RAM. So RAM will not be a problem because database sorting group by they are well managed and they are not you know RAM does not become a bottleneck for them. But these are going to be the problem. So first the CPU will become the problem in this case. Okay, and then disk speed and then disk space and then network speed. All right, now let me tell you how what will happen. Now let's say first, as you start, as your file becomes bigger and bigger, say you got now 1 terabyte of data, you try to sort it using any of these approach number 2 or approach number 3. The CPU will be your bottleneck as well as disk speed. Okay, because as you said, insert will be very time consuming. It is because our disk is slow. Okay, and after a point of time, if you keep on vertically scaling, as in add faster CPU, add faster disk, and you keep on doing that, still the time will be too much. And after a point in time, your disk space will not be sufficient. Okay, that time you might put the data somewhere in the network, and if you try to do sorting after reading the data, if you try to do the counting of words after reading the data from a network computer, it is going to be slow, really, really slow. Okay, and therefore, all these four things will become your problem, right? All these four things will become the bottleneck, and hence the problems with this approach. Now, let me present you a fourth approach. Okay, this is my approach, and this is how lots of people do distributed computing. Okay, this is not truly distributed, but still it's on the same lines. It is called external sort. What does it mean by external sort? We utilize multiple computers to sort our data. In our whole game here, the biggest bottleneck is in this sorting. The biggest bottleneck in this sorting, and after the data grows to a reasonable size, this also becomes your bottleneck. Okay, so general strategy is because this also consumes a lot of time, because disk speed is limited. As you read the data, it takes more time to read the data. So what you do is you read the data, build a cache, build some memory cache, then keep on sorting that parallelly while you are reading it. So sorting and reading generally go parallel to each other, but is still, I mean, on two different threads, and still there is a bottleneck on both the ends. All right. Now, if you take this case, now let me present you the fourth approach. The fourth approach here is external sort, in which what we do is we split the files into small groups which can fit into RAM, and then use approach 2 or 3 or maybe first one on each of the machines and get the result back to the machine from which we launching all of this and give the results. Okay, so user is basically launching its work, sending the data to machine 1 is returning the sorted data. Similarly, machine 2 is also returning the sorted counts. So these machine 1, machine 2 is doing what we had done in the approach number 1, and sorry, and once they return the data, we basically merge them and present to the user, right? So, for example, let's imagine that user has sent sa re to machine 1, and user has sent ga re onto machine 2. Machine 1 returned the count of re is 2 and count of sa is 1, and machine 2 has returned ga as 2 and re as 1, right? and and then here user will do the merging. Now, why did we sort these keys? If you see, re has come before sa and comes before re, meaning the results returned by machine 1 and machine 2 are both sorted. Why? Because merging a sorted data is fairly easy problem. Okay, you can very simply merge the two results to get this one. Okay, you can very easily merge the two. How? You just pick the first value from here. Which one is smaller? You put it in there. I'll show you this part so that you have no doubts. Okay, so say you have one list like this and other list like this. Okay, if you have to do merging of this sorted data, it's pretty easy. You pick up the first one from here and first one from here, right? So which one is smaller out of this? Guy is smaller, so we take it here. Then we compare ray and ray. They both are equal, so we take them together and sum them up. And then we pick the third one. So we were able to easily merge the two data sets by just going through from top to bottom. That's all. So merging a sorted data is fairly easy is to keep the data still sorted, right? If you want to, otherwise, if these machines did not send the results in sorted manner, this user will again be sorting this data and our problem will not be solved, right? Now do you see the thing that we were able to offload the work to multiple machines so that each of these machines can there are 10 CPUs we are utilizing to solve the same problem now, right? So now our response time is going to be far more faster. So do you see any problem with this approach? This is a fourth approach. Now do you see any problem with this approach? Yes. Any single machine failure. Okay, okay, very good point. So what if we build, now this user build kind of a mechanism that if machine 1 fails, then we will basically try to uh, offload the work to machine 3 or something like that. Okay, but it's very valid point. Now second point is, will we have the problem in the size of final file? So size will be huge, but the user does not have to process the file like sort the whole file. All it the user needs to do is keep on picking the first word from all the files and keep on merging together. It will not be too much of a problem. But yes, that's a definitely a problem. That's one of the problems, yes. Any other problem do you see in this approach? User sends one chunk, this is one chunk, to machine 1. User send another chunk to machine 2. Both machine 1 do the computation of the frequency and gives the result in this form. You can see this. In this form to the user. Machine 2 also gives the same kind of frequency of the chunk which was given to machine 2, and so on. And user basically merge them together and then does this. Okay, so instead of user we can call it launcher. Okay, just for, okay, this guy is a launcher. And to your surprise, this is the approach which is being followed in Apache Spark. Okay, and actually we used similar kind of approach when we were building distributed computing at DE Shaw. Okay, now here you can see this sounds like a very brilliant idea, but there are some problems with this approach. Can somebody pinpoint that problem? If machine 2 dies in the process of giving results, back to the launcher. Now, as we discussed, we built one more mechanism in the launcher that machine 2 dies, then we hand over the work to machine 3. But definitely very valid point. Okay, okay. So isn't this same architecture as Hadoop or HDFS? Sort of, but not really. You'll need to look at it a little bit closely. Okay. Okay, Seema's point is if both lists do not overlap at all, will this approach be useful? Yeah, this approach will be sort of useful, but not that much. If the two data sets did not, we could have done other way also. While the launcher sending the data to machine 1, machine 2, we could have separated the data itself. But that is far more trickier problem than the approach which we have taken. What about launcher? If launcher dies, you mean to say? Okay. Yes, that's also a problem. Here, launcher is sending data to machine 1. Launcher is sending data to machine 2. Okay. Notice that part. Okay. How do we decide the division of data if the RAM is inconsistent through all the machines? Very good point. So, generally, the way we generally build clusters is launcher knows how big is each machine. Okay, so that's another point. So you are only telling me that building launcher will be quite a sophisticated task if you consider all these problems. Now Julie has got answer. Communication bottleneck, yes. So launcher has to send this big data to machine 1. Launcher will has to send this big data onto machine 2. And if you recollect, in HDFS, we were already saving the blocks, portions of the data onto each of the machines in our cluster. We could kind of utilize that property of our file distribution. If imagine that our launcher was there, on one of the, we already built something like a HDFS cluster, and if we could utilize the same cluster for this kind of job. We uploaded all our files onto that cluster, and then we build our launcher such that instead of keep on transferring this data every time we need to do processing, we have just transferred it once and it is broken down into pieces and kept on the various nodes. Then we would not have to transfer the data. And other problem with this approach is, so yes, in this approach, final sorting by the values will be again on one machine. Yes, that is very right. So final sorting, as I told you, that final sorting is fairly smooth process because it is not generally in in a sorting. If you are ordering of n elements takes time proportional to n into logarithm of n. Okay, so this is the statistics. But in case of in case you have m m machines and you have n slash m elements on each machines, right? To merge the data, it would take n into logarithm of m. Notice the m. And this makes a humongous difference. This makes a humongous difference, as in, this makes such a huge difference because n is going to be 10 to the power 12. Okay, n is going to be 10 to the power 12. So in this approach, and in this approach, sorry, this m is going to be say 10, and n is going to be 10 to the power say 15, right? So which means this approach and this approach have got a ratio of 15 times. Okay, So the merge sort, to merge the sorted data, it takes to merge the sorted data allocated in m heap m piles, then it takes this much. If you are ordering the elements, then it takes this much. So effectively, the ratio of these two approaches is ratio is 15 times. Okay, which is huge difference. All right. So all right, yes. So that way, the merging will is not generally too big a challenge, but it is definitely a challenge. That too, there are strategies to further distribute it. Okay. Now, the other challenge is, for every time we have a special demand, we'll have to build this launcher again and again. We'll have to program this launcher again and again for different kind of applications. Similarly, l- if we have lot of kind of a problems, like some of you told that what if one worker goes down, second worker goes down, every time we'll have to build all of this fault tolerance, and all of this engineering has to be done. So it requires a lot of engineering other than the network bottleneck. There's a lot of time consumed in the transport of the data, right? So therefore, the only conclusion I have right now is the best solution out of it is use MapReduce. And because that is what has taken care of these two problems as well. Okay. Now, what exactly is MapReduce? It's a programming paradigm. It helps you solve big data problems. It helps you sort big data. It's as simple as that. It helps you sort big data. Okay. And specifically, so when you are building MapReduce, you build a function called mapper, which converts the input data into key value pair. And you need to write something called reducer, which aggregates all the values for the same key together, right? And MapReduce is not only used in Hadoop, it is now a de facto. MapReduce is also used in your MongoDB, CouchDB, as well as Apache Spark. And mappers and reducers can be written in Java, Shell, Python, or any binary program. All right. Now that is what is called MapReduce. Now let's have a look at a couple of examples, and then we will go a little more deep. All right. So let's have a look at a very simple thing. So So MapReduce, basically you write map and you write reduce. Take a look at this simple, very pseudo kind of a programming language we are using here. Don't panic if you don't know this language. Nobody knows this language. Okay. So we have function map. It takes some input and it has this logic. Okay. What does this logic do? In this input, it goes line by line, word by word, and prints word and 1. This is numeric 1, and that's all. Okay, this is our map. All the map is doing is reading data line by line, breaking it down into word by word, and giving out key as word and value as 1, numeric 1. All right. So basically, it took sa, re, sa, ga and gave out an output sa 1, re 1, sa 1, and ga 1. Right. Now, this dashed line is the magic done by our Hadoop. All it did was it took this input, sorted it. So if you sort it, so ga will go up, re, and then sa. and then it sorted and grouped. It did the job of group by. Okay, it did a job of group by. Okay, group by the key. Okay, the key which is specified here. All right, it grouped by that one, but it has not finished aggregating this data. After grouping, it just formed an array. Now how do you want to combine this array into value is your duty. It's taken care by your reduce function. Reduce function takes two parameters, the key and the array. Now in the reduce I can write anything. I can write array.sum, and this is and then I can sum it, or I can say do a standard you do a root mean square value. Okay, so I can do anything with that array, right? Or I can do something like median. I can whatever I want to do, I can write it here. Out what to do, how do I convert, how do I process this array into some value? If I don't want to process, I can say return frequency array. Okay, I don't want to process, I just want to keep it comma separated and be happy with it. So comments go to entire audience. All right, that's why I skip reading it, and it helps me a lot. Only this particular comment which you have sent, Julie, is coming to me. All right, now this is good. This is good because you gave a output in key and value. It got sorted and given by this, and then all right, that's a very good question, Megha. Yes, so this function is yours. Okay, this function is yours. Imagine instead of writing word 1, you could have written it something like 1 comma word, right? Then your output would be completely different. Your output would look like this. Okay, here the only difference is, let me just do some sort of, all right. Okay, so no, it didn't go well. Okay, now here we have this, and now we have this. Okay, now after this step, all of these values will come together because they all have the same key. Okay, if you made one as your key, then all of these values would come together. Now you will have to, your reduce function will be having that. Now imagine that if you, instead of saying this way, you would have put the summation of the ASCII values. Okay, a plus s is some number. Imagine, I can't really count quickly. So imagine 20 plus 1. So, or let's say your word is an inverse of the word. Let's say you are printing here is reverse of the word. Then the way it is going to be grouped is based on this key, right? Reverse of the word, which is AS and ER and AS and GA. So map is your function. If you want to do anything with it, you can write. Okay, and for each word you can also have multiple key values. Okay, so it's completely up to you. Whatever you want to print out of this is your duty. Okay, all right. No, this is a very good question because all of us generally get that impression and then we don't ask that. Because I have faced this question after I finished whole map reduce, and It's good that you asked. All right. Now, same thing. Now, here I demonstrated to you that this is what goes in case there is some magic line happening here. There is this magic line, which is basically grouping the data together, doing a group by. All right. And if there are multiple computers in your network, what happens in case of MapReduce? Okay, let's have a look at what is actually going on. So you have two node 1 and node 2. Just for the example's sake, I have taken this small string. This is going to be something like 100 MB data, or maybe 200 MB data. 128 in the multiples of 128. So node 1 is going to process bigger data than this one. But for example's sake, let's assume that there are only these four words on node 1 and three words on node 2. Okay, don't blame me because it's just an example. All right, now here node 1 is going to run mapper and we'll get this, right? Similarly, node 2 is going to run the mapper as in the previous example. We are going to get this, right? And afterwards, after both the sorting happens, this is going to be in the left leg here at the 3, and this is going to be in the right leg, right? After sorting. And once that has finished, the data is going to get merged and we will get this in the fourth stage. And after that, your reduce function will run on it and you will get the final results. So is it clear to you? So all of this except for these two is your role. Okay, rest of the mechanics is by Hadoop. The merge is happening on a single node. Now question is which node to select to do the merge. Generally it is the one which is free. Okay, and sometimes we choose this merge on one of the nodes itself, node 1 or node 2. Why? Because some of the data is already local here. So while transferring here, if you see this line, it is basically a transfer of data from node 1 to this node containing the merge. Now, similarly, the data from node 2 is a separate computer as well as node 1, and the transfer is again a network call. So, to minimize it, we could actually do the merge on one of the leg itself, one of the node itself, and it will be little efficient. That is, those are the optimizations Hadoop keeps on doing all the time. All right. So Hadoop generally do the merge on one of these nodes. Was that your question? Okay, good. So sorting is something which keeps on improving all the time. And sorting is an algorithm. Every year there is one new sorting. Okay. So the sorting which we follow here is basically external sorting. All right. And sometimes the data division itself is a different strategy in different cases. Okay. So basically in case of MapReduce, they have their own sorting algorithm which is somewhat based on the external sorting. Okay, all right, sounds good to you. Should I move ahead? So this is the case where we have a single reduce. We could have multiple reduce like this, right? So you have node 1, node 2, up to the here everything is great, up to merging it's great, but afterwards there is a split happening. We call it shuffle. The split is happening like this. Okay. So some of the keys go to one leg, some of the keys go to another. But one key goes to the one side. If you see, RE has gone to left while all the SA have gone to, sorry, RE has gone to left while SA has gone to right. So the shuffling approach, the shuffling step ensures that all keys are together and the load is divided equally into multiple reduce machines. If you have multiple reduce, okay, so while you are launching a job at Hadoop, you will have to tell what file do you want to process, what is the definition of your map function, what is the definition of your reduce function, how many reduce do you want. Okay, but do not specify how many mappers do you want. Okay, that is decided by itself. And can somebody quickly remind me on what basis it decides how many maps are going to be there? Here we have shown only two maps, one left, one right. Okay, how is it decided? As we said, number of data nodes on which data is. Perfect, perfect. Yes, based on how is your data located. Okay, that is something in the hands of Hadoop to decide. Now most of the work in the reduce can be divided into multiple nodes. Okay, because sometimes aggregation takes time. Sometimes aggregation takes time. All right, so this is just one example case where we have taken step by step just to understand how does map reduce happen. On a larger scale, you can think map reduce as a big group by. Like what you do in map is selecting what is going to be in the output, what is going to be the key, and what is going to be the value. And in the reduce, you basically operate upon each group which is formed by this key. Okay, so that is what it is. All right, so group by essentially is very similar to what we have as map reduce. All right, so sounds good to you? So effectively you will be converting your problems into group by, into group by kind of a paradigm. All right, now we have few questions for tomorrow and we will discuss these questions. So do you have any questions for me before I move ahead? As an example, actually that will be a complex example. So in case you are interested, you can have my matrix multiplication, which I wrote as part of mm, how would you multiply two big matrices? How will you multiply two big matrix? Okay, using MapReduce. So this is my approach. This is one of my approaches to solve that. And we'll discuss. So actually what I wanted to do is take one more example because somebody yes in the last session told me that they wanted one more example. So I'm yet to come up with an example. So if you guys can come up with some example, I can give you quickly. Okay, so I think okay, Ranjit is not able to hear anything. Is anybody else having the problem with the audio? All right. So Ranjit, okay, yes, merging will become the bottleneck sometimes, and that's when if the merging is becoming bottleneck here, so this merging is essentially very federated model. Generally, what happens is in this form actually, will show you. This is just for conceptual one. So the way the merging happens is this. Okay, what you do is, yeah, so what you do is you sort the data on each machine and then copy it to the reduce. Okay, and then you merge it, right? But if you have multiple reducers parallelly, okay, I should have uh, yeah. So this diagram, I think I should keep it here as well. One more. All right. So here, if you see this, you take a look at this. What's going on here? If you have multiple reduces, so some of the keys are directly going to reduce number two. Some of the keys are going to reduce number one. Some of the keys from each of the mapper node, the data is going to two different reduce. So this way, they have actually solved the merging step. Now merging will be happening only one part of the data. And this division between what goes to reduce one and what goes to reduce two happens on the node itself. All right. Very good question. Any other questions? So therefore, this diagram is little bit hacky. Okay, this diagram is little bit hacky. I've just, you can think of it some magic happening and merge shuffle basically divided it. Yeah. Any other questions you have for me before I put questions to you? How does the mappers coordinate to send all the same words to the same reducer? That's a very good question. Okay, so there are two answers to it. I'll again jump to the same diagram which we're talking here. So if you see, basically there is a division already happening on each mappers. This division happens, there is a fixed algorithm in all three nodes which divides the data, right, based on ASCII values of the keys. Okay, based on ASCII values of the first character of the keys. I mean, just as an example, but that's that algorithm of splitting the data, the keys, is more sophisticated. That is how it generally happens. Now, MapReduce comes up, gives you that flexibility of dividing the input data by yourself. Okay, so the sections which each mapper is going to form are going to have same set of data. Regarding the current diagram, we have reducer for every mapper. No. Number of reducer and number of mapper is going to be different. But if you mean to say that of every data, no matter how many mappers are there, going to be through some reducer, then you are right. We have reducer for every mapper. Okay, okay. let me yeah let me answer Gaikwad's question again. All right. So he says that how does mapper coordinate to same same keys? Okay. Word means keys, right? To the same reducer. Now let's imagine this. It's pre-decided on by each mapper that I will send. If there are n mappers, I will divide the keys into n sections on the number line. Okay, so let's say for alphabets from A to Z, if the values are less than k, they will go into one part. If if keys are less than k, they will go into one section. If keys are greater than k, then they will go into another section. Now imagine the same logic embedded on all mappers. If less than k, go in one. If greater than or equal to k, go in another. Now same set of words in all the portions. There are two parts, part 1, part 2. Okay, part 1 contains only the keys which are from A to J, while part 2 contains K to Z, right? Similarly in all. Now the part 1 from all of these mapper is going to go to the first reducer, and part 2 from all the mappers is going to go into the second reducer, right? That's how it works. Which means which means all all the now basically A to J will be in the reducer 1 and K to Z will be in reducer 2. Perfect. Great. Now let me again read out Seema's question. Regarding to the current diagram, we have reducer for every mapper. Okay. All right. Is that correct? Then one reducer at the end. Yeah. So at least there has to be one reducer. I mean, not necessarily. Sometimes reducer doesn't do anything. If you don't write anything in reducer, that's okay, fairly okay. The result will be comma separated and will go in the output. All right. Now, next question is also one more thing you should remember is that you don't necessarily need to write a reducer function. Okay. Does it happen? Does it depends on the size of the data? We have number of reducers. It depends on how many blocks are there in your input data and on how many machines it is located. So generally, the bigger the data, more machines are going to be used for your data. And hence, oh, sorry, I answered a wrong question. I answered that why do we have uh, does the size depends on the mappers? So yes, mappers is yes. Does it depends on the size of data? Yes. So two things which matter for your number of reducers, and it's actually very difficult to answer. Question is how do we decide the number of reducers? So you decide number of reducer. By default, generally a reducer is one. Okay. So so if the data is big, okay, then then your churning will be higher. Okay, your merging will take more time and so on. Therefore it is wise to actually have multiple reducers so that the the churning is distributed. Okay, so but as you increase number of reducers, the network traffic starts going up. As you can see, the total number of these lines is number of mappers into number of reducers, which is 3 into 2. It is 1 2 3 4 5 6, right? So if you increase number of reducers, then network traffic goes up. If you reduce it, then the uh, load on each reducer will be too high. So you will have to do a little bit of heuristics in your case, to figure out how many reducers are good enough. All right. So I think I've answered Amit's question also. So the result of sort goes to reducer, and the result of reducers. So the result of sort goes to reducers, yes, and the result of reducers to back to reducers. And okay. So this is interesting. Okay, here the answer here. So this reducer is not called recursively, unlike the other functions. Okay, reducers is called on all the data together. Okay, so yes, that happens in some systems, not in MapReduce, but that's a very good point. So what she meant to say is, do we keep on reducing data again and again till we reach the point? Answer is no. In case of specifically Hadoop MapReduce, the output of reduce directly goes to HDFS. Okay. While in case of Apache Spark, the method reduce we keep on calling method reduce until we get a singular value. Okay, but here the output of reduce directly goes to HDFS. Okay, okay. So Seema's question is that can we do some sort of reducing on the mapper level so that it is faster? Yes, that's a very good point. That is why I'm pretty happy that you have come up with this question. This is a very brilliant question. That is why mm, Hadoop guys came up with something called combiner. That's exactly what combiner does. Okay, that's exactly what combiner does. So what you mean to say is that there will be a lot of, before transferring the data, we want to do some sort of churning on each of the node. Okay, if you want to combine or reduce the data here itself, then it could have been faster, right? So yeah, so that is something called combiner. And interestingly, the signature of combiner is exactly like the signature of reduce. It takes key and values and then reduces it. All right. So good, good. I'm pretty happy. Can we have a small real-time example that explains MapReduce functionality, like the fingerprint recording function and guessing the age you were talking about? Okay. So those kind of things, fingerprinting and guessing the age, is sort of a little bit of machine learning involved. Here we will take a very simplistic case. Okay. We have enough time. So how should I? I'm just thinking about something. I think I would take an example from my problem itself. All right, this will be easier. I'm doing a little bit cheating here. I'm taking the easiest out of the lot. Okay, so the question here is, there's a file that contains the DNA sequence of people. You have to find all the people who have same DNA. I think you guys can tell quickly what key values will mapper will give us. Yes, what should our mapper give here? Yes. So if your mapper, so if you have this input data, right, and all your mapper did was, uh, your mapper did emit value, comma, emit DNA, comma, user. So our overall output will look like something like this. Okay, our overall output will be something like this. It'll be ACGT, and then user 1, and then TGCA user 2, and so on, right? TGCA, then, okay, all right. So and then it will basically bring user 3 and user 5 together. So all I did was I did a quick regex thing to replace a column 2 with column 1 and column and so on. So these two will go together, right? Oh, I think I made a mistake somewhere. All right. Yeah. So user 3 and user 5 go together and so on, right? That's all. This good enough? So basically we brought these users together without actually iterating the data. Ideally, what if a usual programmer, what they will do is they will form a hash map, read this into the key, and then keep user one as a value and then do it. And this would lead to a lot of memory usage and it will not lead to the results, right? That kind of problems cannot be solved if you try to create a hash map programmatically, read line by line into the memory, put each key and the value, and keep on doing it. Then all of the data you will end up reading in the memory and it will become a big hassle. And trust me, most of us actually forget. Even I have seen many Hadoop developers, they end up mistakenly do a lot of stuff in the memory instead of delegating it to the MapReduce. I've seen it multiple times. All right. Now, I have here there are four different problems. First is you have to compute frequency of letters. Okay. Instead of frequency of words, you have to just count the frequencies of A to Z. Okay. A to Z, it is all small characters. For capital also, it's the same letter. Whether capital or small, it's the same letter. Okay. All you need to do is do the count the frequencies of the letters instead of doing it for the words. Now, do you need MapReduce for this? If you need MapReduce, then what is the size beyond which you might require MapReduce, and what is the size below which you will like to do it on your machine? Just, just your gut instinct. Okay. This is also, yeah. So can we use regular expression logic within map function to sort at mapper level? Okay, okay. The problem is, to the mapper, you will be given only one line at a time or something of that sort. but you can definitely use any of the computing logic which is available to you. Okay, to an extent you can do something like contact an rdbms database from within the mapper and get the data from here and there. Try to do all sorts of things including sending email, because mapper is your standard programming language function. You can do whatever you want to do in that function. Okay, did I answer your question or? Okay, now this is my first question. You have to answer this question. Second is you have to find the anagrams. So you do it over the week. Okay, think about these problems. You are given a huge text. You have to find anagrams. Okay, say for example, anagram is a rearrangement of the same letters. So the the has no other anagram in this, but cat, act, and tech are anagrams of each other we want in this format, and there is no other anagram, right? So given a huge input text, maybe imagine like you have got 1 terabyte of such data. Now you have to compute. Say you downloaded whole wikipedia and you want to find anagrams of words in the wikipedia, then what are you going to do? Okay, sounds good to you? All right, all right. Now, yes, you have to solve these problems in terms of MapReduce only. What will, you don't have to write a program or something. You just have to theoretically write that my mapper will give this key and this value, and this is going to be the logic inside my mapper, and this is the logic which is going to go in my reducer. Now, next problem we have already solved. Now, the portion of third problem is little difficult. It says a file contains a DNA sequence of people. Find all the people who have either identical DNA or a mirror image of DNA. For example, here user 1 and user 2 and user 4, okay, they either have same DNA or they have the mirror image. User 1 and user 2 have mirror image of each other. It is ACGT, right? Is mirror image of this one. So user 1 and user 2 as well as user 4 you have to bring together, while user 3 and user 5 can stay separate. Had it been something like user 6 and we had AC, C and T, right? Then in that case user 6 could have been alone, okay, like this. Now this is what you have to do. How would you form your key such that these users come together? Think about it. Think about all the ways you can solve this problem. Now, next problem, and remember that this is a huge file. These are the DNA prints of whole world, right? Okay, now next problem here is, okay, let me have a look at the course page. This is your course page only, right? Assignment. No, actually I will enable here you will see a link where you can actually paste your answers in the in the window itself. Okay, so you start doing your work. In this assignment, link will be enabled. When you click on that, you will, like a quiz, you will have to submit on the website itself. You don't have to send an email to me. Okay, All right. Now look at the fourth problem. This is probably a little more difficult, and to your surprise, this is the reason why whole the biggest use case of this problem was, I mean, the biggest use case of MapReduce was actually this problem. In an unusual democracy, everyone is not equal. The one who is richer has got more vote count than the poor one. Okay. Now, in this unusual democracy, everyone is voting for the other one. Okay. Now, the vote count is a function of the worth of the voter. If A was a worth of 5 and B with a worth of 1 are voting for C, then the vote count of C is 5 plus 1. And you are given a list of people and their value of the vote. You are also given another list describing who voted for who, right? So think of this way, we know we know who voted for who, and we know the worth of each individual in this society. Now we want to compute the vote count of each votee. So C got voted by A and B. That means C's vote count is 6, while F got voted by C and F's vote count is 11. A and B did not get voted by anybody. Their vote count is 0. Sounds good to you? Yes. Good. Good. So there are these four problems which you got to solve. And if you have any doubt, drop me an email and or call me on our number. Okay, here is the number. All right. So that is pretty much for today. Okay, we will meet on the next Saturday at the same time, and we will take the discussion further. Okay. Do you have any questions for me? We still have some time. Either I can start the next session, or we can discuss some of the questions. Slide number 17. Okay. Wow, you remember the slide number 17? Okay. It does restore the results, don't worry. It restores the result. So when you submit at the last, that results get submitted, and when you attend next time, you can the result on your end will get reset, but I have the record. Okay. So Abhinav's question is, okay. So Abhinav's question is that why is the output of reducer going to HDFS? Yes. So basically, the input to the whole system came from HDFS, and hence the as a design principle, because when we launch a map reduce job, we generally launch it and forget about it, or we keep monitoring it. We do not wait right away that we'll get the response. Okay. Once that is done, and it doesn't return the value to the guy who launched it. It doesn't return. Why? Because the user, it's a passive job. This is something which runs for longer time. The user cannot wait for that. Therefore, MapReduce has to put it somewhere. And what is the better place than keep it in the HDFS? The other benefit of keeping it in HDFS is, maybe we have a chain of MapReduce sections. we have chain of MapReduce phases. Okay, there's another MapReduce which is operating on the output of the reduce, and therefore it made a lot of business sense. It made a lot of sense to put the output of the reducer into the HDFS. Okay, do we have to write mapper and logic, reducer logic, or so you can, if you present it in diagrammatic form, that's also great. Okay, and either way is fine for me. Okay, the better thing would be, because if you put it in a diagrammatic form, this thing, the one which we are using, the rich text format, is not actually accepting the diagram, so it might be a little difficult. Now we still have like 6 minutes. So yes, Hadoop is always used for batch-wise operations because there is a latency involved in launching every job. It takes some time to distribute the work, sometimes to load the data, and sometimes to gather the results back to the reducer and then saving it. So there is a latency involved. Therefore, people prefer it for sort of a batch jobs. Okay, but it is probably the platform to handle the biggest data possible, right? Any other questions for me? We are talking about a latency of maybe 15 seconds to 20 seconds, or maybe more. Because in case one task tracker fails, then the work shifts to another one, and then there is a lot of logic which goes on. All right. So 10 to 15 seconds is usual. And sometimes, if we are talking in terms of Hive and other stuff, 5 to 6 seconds is quite normal, even for the basic queries. Okay, how about search engines then? So search engine do not use MapReduce or any of these MapReduce or Hadoop kind of systems for users query in live. What they use it for, probably the backend jobs such as computation of page rank, or doing some sort of analysis of the corpus downloaded, or maybe the crawling part, the phase on which it doesn't it doesn't impact the end user. That's where these people use. All right. Okay, the result in HDFS replication is retrievable. The life, it is retrievable for lifelong. Okay, it is not a temporary storage. It's lifelong, as in as long as you don't delete it. It's for good for reporting analysis. Yes. Then for real time search results, can we afford that latency? I think I have answered it. Is the latency holds good for no? HBase is far faster than any of these things. Although HBase runs on HDFS, but HBase is designed for humongous performance. Okay, can you please tell some of the real time MapReduce examples which you find challenging and interesting? So if you want to try out, try the matrix multiplication using MapReduce. Trust me, it is going to be humongously challenging. Okay, try the MapReduce on matrix multiplication. Think about if you have million rows by million columns or billion rows by million columns, then how would you multiply such matrix? All right. Amit's question, good for reporting analysis, yes. And Cassandra or HBase, that's a huge debate. If you have HDFS already in place, I would suggest HBase. If you don't have HDFS in place, go for Cassandra. I mean, that's a straight, blunt answer. So if we use MapReduce against data, we need to know the questions we are answering before we start. Exactly, exactly. We need to, if we use MapReduce against a data, we need to know exact questions and before we answering and before we start. Yeah. But as a thumb rule, in probably every organization which plans to move to big data, whether they use MapReduce, Hive, HBase, Cassandra, anything, everybody ends up having at least one HDFS cluster. All right, all right, great, great. This is the most wonderful class, and I have a great set of candidates in the class, in this particular one. I'm pretty happy about it. All right, then have a good week. And if you have questions, drop me an email at Sandeep at no big Hadoop at no big data will be a better one because we are tracking that one. All right. So I'll be sending you a questionnaire to see how did I mean, probably Anjana would be sending it, and please respond to the questions. It'll just take your 10 seconds of time. All right. All right. All right. I will try my best to keep you awake at least. And yeah, have a good week ahead and bye bye.